In this lecture, we will talk about how do we use some standard 7400 series ICs to design a counter. So we'll take a look at counter application. We'll start off with a simple design, and then we will build on that. We will try to cascade counters and so on. So before we do anything, what is a counter? A counter is a sequential element, one of the simplest finite state machines that is going to allow us to count, and the term count refers to the output of a flip-flop. So let us begin with talking about how to use this 74X163. This is the same chip that you guys are using today in studio. And let's see if it can help us design a 4-bit counter. So the schematic of the chip is shown to you. There are lots of inputs. Let's go through them one by one. So first of all, we have a positive edge triggered clock. So I'm going to try to go this way. I'm going to try to go this way, counterclockwise, and I will I'll try to describe each and every pin here. So let's say the topmost was clock, right? So let's say 1 CLK, and for CLK it is pretty straightforward because it's a positive edge triggered. That means that the output of the counter is going to increment by 1 soon after the positive edge on the clock input is observed. So the output of the counter, if I may add another page here, let's see. So the output of the counter, and we are calling the output of the counter QA, QB, QC, QD. Those are the 4-bit counter values. So that's the 4-bit output. And there is also a ripple carry output, an additional output to monitor something else. We'll talk about that in just a minute. But QA, QB, QC, QD are the outputs of the counter that we would be interested in. And we know that it's going to count by observing those values. So QD, QC, QB, and QA. Notice we are using the letter Q to indicate the output of the flip-flop, just as we did in registers and flip-flops, as well as in latches. So these are just true forms of the outputs. And it is going to count, when it counts, the increment is going to be in this form. QA is the least significant bit. So it's going to go 0, 1, 0, 1, 0, 1, and it is going to keep doing that for 16 rows in a free running setup. So this is in the free running setup. And QA, if it's the least significant output, it's going to alternate every positive edge. QB is going to be half the speed. QC is going to be half the speed of that, 4 zeros, 4 ones, and so on. And then QD, of course, is going to be the most significant bit with 8 zeros and 8 ones. So we have the most significant bit of the counter here and least significant bit of the counter here. And if you observe, that is decimal 0, that is decimal 1, that is decimal 2, that is decimal 3, and so on up to decimal 15. So this free running oscillator, this free running counter if we do no manipulation to this, it is going to count 0 to 15 and it is going to go back to 0 to 15, right? So its counting pattern is 0 to 15, back to 0 to 15, back to 0 to 15, and so on. It'll keep running. But that increment from here to here or from here to here happens when the clock goes up, right? The positive edge of the clock. Soon after that, the counter is going to increment by 1. So that's what we are talking about in terms of the outputs and the clock here. Let's go back, take a look at, so the clock input we have talked about. I need to connect that to a timing source with some period, right, which goes up and down, and every time a positive edge occurs, the counter will increment. The second pin on the left is clear, and clear is actually a active low input, right? So it's an active low input, and it is used to clear the counter, which means that I can make all these guys 0, right? So I can make these guys 0 if I connected this to ground, for example. So if I activated clear and a positive edge on the clock is observed, then the outputs of this chip will go to all zeros. They get cleared. So it's an active low input, and I should also add that it is in sync with the clock. So it's synchronous. So it also depends on the positive edge of the clock. So that's your clear input. Let's go down here and talk about the third thing. What is your third? LD. That is active low. It's an active low input, and it is also synchronous with respect to clock. And what it does is it is going to load. It stands for load. So it's going to load whatever you connect at A, B, C, D into the counter. But it is going to load that only after the positive edge of the clock. So I can write that this is load, and it is used to, so maybe in red I can say used to load an arbitrary counter value. But that value will get loaded into the counter. Whatever you connect over here will appear over here after the positive edge of the clock, as long as the load is active, meaning connected to low, because it's an active low input. All right, so let's move on to 4. Well, I can combine ENP and ENT. Those are my 2 active high enable signals. So these are my 2 active high enables. And we are using 2 of them because it allows us to gain more control over the cascading of such chips. So if you wanted to make a 8-bit counter using 2 4-bit counters, we would be able to do that. And during that process, we would use these 2 enable signals in a smart way. So those are my 2 active high enables. Only when both of them are enabled, the counter is going to do the counting or incrementing. Next, 5 is your 4-bit inputs, 4-bit data input. So those pins A, B, C, D, with A being the least significant and D being the most significant, that is just used to load whatever the user wants into the counter, right? So this is used when user wants to load arbitrary inputs into counter. So let us suppose I wanted to load the decimal value 3, right? Let's just suppose, for the sake of an example, I wanted to load the decimal value 3, right, into the counter. What would I need to do? Well, I would need to, among other things, I would have to not use clear. So that means I would have to make sure that the clear input is inactive. I would have to make sure that the load input is active, right? I would have to connect that to ground because I'm trying to load 3 into the counter. I would have to make sure that enable signals are active. In fact, the load happens along with a particular input. So enables are active. ABCD is connected to 3. So least significant is A. So I would connect that to 1, that to 1, that to 0, that to 0. So that's my 3. And I'm assuming that load is active. And then if I see a positive edge on the clock, all those values will appear over here, which means that I will be counting 3 in decimal at that point. So that's how you load an arbitrary value into the counter. We'll see more examples on that in just a bit. All right, so we have gone through the left hand side. Now let's take a look at number 6 here, which is the things on the right. QA, QB, QC, QD are your 4 true form outputs of the counter. 4 active high outputs, which are essentially telling you the value of the counter, right? Current value of the counter. And I should also point out that QA is the least significant bit and QD is the most significant bit of the counter. The input is, so there's a question on the chat box. The input is where the timing cycle is going to start. The input. The timing, all the timing related things are clock related, right? So whatever you connect to pin number 2. So the first positive edge, that's when everything gets into gear. All right, so at this point, let me ask you guys, well, let's finish this first. Let's finish talking about 7. So I have got my 4 active high outputs that indicate the value of the count, which is essentially based off of this table, right? It goes from 0 to 1 to 0, 2, 3, 4, 5, and it keeps going 0 to 15 and back to 0 to 15, and it keeps repeating in that pattern. If it was connected in a free running setup, the way it is right now, right? Just connect the deactivate clear, enable the chip, and give it a clock. That's it, and then it'll keep counting. But we could also do other interesting things with it. We'll take a look at that later. Now let's take a look at the last output over here, which is 7, which is the ripple carry output. Very helpful in cascading counters. Helpful in cascading. So if you wanted to build bigger counters using this chip, then that particular output will be very handy. So RCO is an active high output, and it becomes active only when all outputs QA, QB, QC, QD are 1. So that means that when the maximum count of this counter happens, 1 1 1 1 or decimal 15, then that is the time this output is going to be a 1, right? So it is just indicating to the user that I have reached my maximum value. And it also becomes active high. There is another enable that has to be asserted in order for RCO to become active. ENT has to be active here, has to be active. So RCO becomes active when all the 4 outputs are at 1 1 1 1 and the ENT has to be active at that time. Okay, let's take some questions about just the inputs and outputs for this 74x163. So the question is, will the chip work only if one of those no, both enables have to be enabled in order for it to count, right? You don't need to enable it to load things into it, but if you want the counter to move up by 1, you have to enable both signals, both enables. You have to make both enables active. Next question is, if only need to use one counter, do I only need to turn on one of the no, both enables. So this is only, so this statement is only with respect to the output, only with respect to the output, RCO, right? So if you want to observe the maximum count value, then you have to make sure that when that happens, ENT is also active, right? Because there is also a possibility that the counter is at 1 1 1 1 and the ENT is inactive, right? ENT has to be active in order for it to be counting, right? If it is not counting and it is just staying there at 1 1 1 1, then the RCO could be high, could be low. That depends on ENT being active or low. Yes, with respect to ENP and ENT, it is just with respect to the RCO that they are different. You got it. Yes, ENT being active indicates that there is a carry, which means that I have completed one full cycle while when I was counting. So RCO becomes active. It means two things. One is the counter outputs are at 1 1 1 1, and also ENT is active right now. But in order for the counter to move up even by one value, 0 to 1, 1 to 2, and so on, both, if it has to move up, both the enables have to be active at that time. All right, other questions? All right, so you see, if we just want to get the output. So if you just want to get the output, the only active ENP is so here, let me clarify this. Add a page. If you want to count, then you need to make ENT enabled. If you want to count. What does count mean? Count is 0, 1, 2 to increment the outputs. But with respect to RCO, it will become active when the counter output is at 1111 and also ENT is active. We will see later on how this is useful in order to cascade. What is it? Yes. So it's with respect to the cascading of counters. So we'll take a look at an example, later in the lecture where you will see this play out. But the moment you see more enables than necessary, it's being done for that so that the user gets more and more control over the design process. But like I said, there are two enables over there that will help us with the cascading of 74x163. We need to make sure ENP and ENT both on, so we got input 1111, RCO will be 1, otherwise it will output 0. Let me take a look at the comment here. We need to make sure ENP and ENT are both on, so if we get the output 1111, RCO will output 1. Yes, otherwise it will output 0. Michael, you are absolutely right. So both enables have to be 1 in order for it to count, and during that counting, when it reaches 1111, RCO will output a 1. And if during that time, when it reaches 1111, if ENT is inactive, RCO will not output a 1. All right, so these are summarized later on as well. We'll take a look at that. Okay, so let's move on. We talked about the counter and how it goes. Let's see. So let's take a look at some counter operations. First, we have the 74x163, and we have connected a few things to it. We have connected a clock to the positive edge triggered clock input. We have made sure that clear and load are connected to high using a pull-up resistor. That means that I'm never clearing it and I'm never loading anything into it, right? I'm not and I've connected both the enables to the high. So this is enabled. It will never clear and it will never load anything into the counter. A, B, C, D are left unconnected because I'm not using load, so I can leave them unconnected here. And then QA, QB, QC, QD are the 4 outputs along with the RCO that I'm monitoring for this free running oscillator, free running clock. So it's free running or divide by 16 or mod 16 counter operation, right? So this is mod 16 because it will count from 0 to 15, 0 to 15 and so on. It'll keep running in that pattern. And as I said, count if ENP and ENT both are asserted, both have to be asserted for it to count. You can load if LD is asserted. In this diagram, it is not, but load overrides counting, which means that if you have the counting going on using the enable signals, you can stop that counting and load some arbitrary value into the counter when load is activated, which means that load input has priority over counting. Next, clear, that is used to make all the outputs go to 0. Clear if CLR is asserted. So if clear input is made active, then you can make all the 4 outputs go to 0. And this actually has the higher priority, even higher priority, overrides loading as well as counting. So in terms of priority, clear has the highest one, and then loading, and then counting. All operations take place on the rising edge of the clock. We have talked about that because it's a positive edge triggered counter. And then your RCO is asserted if ENT is asserted and the count is 15. So 1111. Now I should point out one thing. What would happen if I connected this and I started the clock? Can you guys tell me this? So what would happen if I connected things just as I did right now? Can you guys tell me what will be QA, QB, QC, QD to begin with? Like what will be the first counter output? Uncertain is absolutely right. I do not know what will be the output. So what do I need to do? Load is one option. A better option is to use clear, right? So if I clear first to make them 0, 0, 0, 0, then you make clear inactive and count. You guys see that? So if you make clear, say you may, instead of connecting it to high, you connect it to low first, maybe using a binary switch, you can control clear. Connect that to 0 first so that your outputs go to 0, all of them, and then you make clear input inactive and then let it count. You guys see that? Now this will play a crucial role in the studio today. Now because we are simulating this counter, uncertain is not an option, right? Uncertain means X. You will never see the counter move. Even if you connect everything properly, and if you have set up everything about your simulation correctly, if you do not know how to get things started, then the counter will not count. So make sure in your LogicWorks simulation, you use a switch to control clear, make it 0 first, so that your outputs go to 0, 0, 0, 0. Then you can toggle that particular switch to 1, which means that clear is inactive, and then you can start the counting process. Question on the chat box is, then what will be the output? Only 0 or count to 15? So when I clear it, it will be 0. Then if I want it to count, then I have to make it inactive, right? So if I make clear inactive, if I make load inactive, I enable the counters by connecting ENP and ENT to high, then it will start counting, right? So first I'm making things 0, right? So when I start, I'm at right here. When I start, I'm at 0, 0, 0, 0, and I stay there for some time because I will have to wait for the user to make clear inactive. The moment clear becomes inactive, then it will go to 1, 2, 3, 4, and it'll keep going from there. And it'll go to 15, back to 0. So once it starts off, it will go through that pattern, 0 to 15, 0 to 15, 0 to 15, and so on. But if it has to count, clear has to be inactive. So I would say use a switch there to toggle between a 0 and a 1 for clear. Make it 0 first to load to clear the counter. Then you connect the clear input to 1 so that it can count. Other questions? Now in simulation, you have to do this. In practice, you don't have to do this. In practice, it would it would randomly power up, right? So in practice, what is the reality? The reality is, if you don't clear, then it will start at some random power up state. Maybe 10, maybe 14. It will start at some random power up state, and then it will go into that loop 0 to 15, 0 to 15, 0 to 15, and so on. So that's the reality. However, in simulation, it cannot do the random power up state. So in simulation, in LogicWorks, you have to use clear or load to get it to start at particular value. I recommend using clear. All right, questions now? Okay, so this is, this is an example where things are going between 0 and 15, right? So all the 16 output possibilities are being covered in this setup. But that is not necessary. That you can do something else with it as well. And we'll take a look at that in a moment. These are the timing waveforms for this divide by 16 counter or the mod 16 counter. Mod 16 meaning that there are 16 different states. You have the clock input at the very top. It's a positive edge trigger design. So every time there is a positive edge on the clock input, QA is the least significant output. So that toggles every time there is a positive edge on the clock. QB is the next most significant output. So that toggles every 2 positive edges, every 4 positive edges, every 8 positive edges of the clock. So QA, QB, QC, QD. Now if you take a look at 0, 0, 0, 0, then you have 1, 0, 0. So that's 1, and that's 2, and so on, and it'll go all the way to 1, 1, 1, 1, which is decimal 15. And if you can see, RCO becomes high only when the count is 1, 1, 1, 1 and ENT is 1. So that is an assumption that is being made here and not explicitly shown, that ENT is 1. So ENT equals 1 here. That's an assumption that we are not explicitly showing. So I just want to write that out. And then it will go back to 0. So it will go into that loop 0 to 15, 0 to 15, 0 to 15. Now that loop could have been 1 to 15, back to 0 to 15, 0 to 15, right? So the loop will be 0 to 15, but depending on how you have initiated things, it could start up in some power up state, maybe 4, maybe 10, but it will eventually go into that loop of counting. As long as all the other control inputs are taken care of, like the enables and so on. All right, let's do more interesting things with it. Now, this particular example is about how you can load 15 after count is 15. Load 5 when the count is 15, right? So the counting sequence here is 5, 6, 7, go up to 15 and come back to 5. 6, 7, go up to 15, come back to 5. So in this particular example, we are using the same 74X163 chip, but with a slightly modified output counting sequence. Whenever we reach 15, right, the design idea is this. Load load 5 into counter when QA, QB, QC, QD are 1, right? So when the counter reaches 15, load 5 into the counter, right? So for this, what did we do? Well, we are trying to load 5. How are we loading 5? Let me highlight that in blue. Load 5. How are we loading 5? Using the load input as well as A, B, C, D. As you can see, A is the least significant bit, which is connected to high here. B and D are connected to low, and C is also connected to high. So I'm just going to simply say this is 1, this is 0, this is 0, this is 1. What is that? 0, 1, 0, 1. That's 5, right? So we are loading 5 by doing that. So we use load like that, and then like that. And then how about the enables? ENP and ENT, they are both connected to high, so it's enabled. The clock input is connected to the timing signal called clock here. Clear, which is an active low input, is connected to high, which means that we are never clearing it, right? We are never clearing it. Now notice what happens. RCO is the output which tells us that there is 15 here, right? So if it is 1, 1, 1, 1, and this guy is already connected to 1, so that's good. This is going to become a 1 then, which means at that time this is going to become a 0. That means that we are going to load at that time when it reaches 1, 1, 1, 1. What are we going to load? Whatever you connect at the inputs A, B, C, D, which is 5. So that's how we load 5 into the counter when it reaches 15. We just had to put an inverter over here because RCO was an active high output and load was an active low input. So we had to put an inverter over there. So this is going to be 5 to 15. So those are 11 different states. So it's a divide by 11 counter. Note that 4 to 14 would have also been a mod 11 counter, right? 5 to 15 is 11 states. 4 to 14 is also 11 states. So that is also a mod 11 counter or divide by 11 counter. Questions about this? So the first example that we saw was free running counter, 0 to 15, 0 to 15, and so on. The second one was start at some user defined value, but stop at 15. So as usual. So what if I only want to count from 0 to 5? Right. So we are coming to that in just a moment. So, my answer to your question is clear the counter when the counter, load 0 into the counter when the count reaches 5, right? Load 0 when count reaches 5. So we will have to figure out a way to detect 5. Questions about this? All right. Now this is another way to design a modulo 11 counter or divide by 11 counter. In this case, we are using 0 to 10. So this is very similar to the question in the chat box about 0 to 5. So what are we doing here? We are clearing after the count reaches 10, right? So we clear the counter right after it reaches 10. So clock as usual, clear connected to, no, I'm recording using some other software. Clock is connected to the clock input here. My load is connected to high, which means I never load, always enabled, right? Never load, always enabled. I'm only using clear here. So what am I doing? I detect 10. When I detect 10, I clear the counter, right? Clear counter when you detect 10. So how do you detect 10? Well, for 10, QD, QB, QC, QA. That is 1 0 1 0, right? And as you can see, QD is 1 and QC is 1. 10 is the first time QD and QC will become 1, right? So 10 is the first instance when QD equals QC equals 1. So if you are starting from 0 and you are counting up, the moment QD and QC why did I write QC here? This is QC, this is QB. So the moment QD and QB become a 1, that's the first time that indicates that 10 has happened. You don't really care about the other two outputs in this case. So you take QB, you see that? You take QB and you take QD and go through a NAND gate, because that is going to take in 2 1s at that time and give you a 0, which is used to clear the counter. So as soon as you clear the counter, the outputs will become 0 0 0 0, and when they become 0 0 0 0, this will become a 1 there. So it will never not clear now, right? So this is another way to get a modulo 11 counter, but in this case the new thing is you are starting at 0 and ending at an arbitrary value. So first example, free running. Second example was to start at an arbitrary value. The third example was to stop at an arbitrary value. And of course, you can guess the last one is going to be to start and stop at some value other than 0 and 15, right? So something like 1 to 9, for example, the thing that you have for your studio today. Let me take a question on the chat box next. Does the clear occur before load? Clear and load are both user inputs, right? So it depends on when the user chooses to activate clear or load. Because if we wanted to achieve 1 to 9 counter, wouldn't we need to track the output and use that for loading, right? Not clearing, for loading. Because we want to start at 1, right? So we don't want to start at 0. So we cannot clear. We have to load it. So if you want to go from 1 to 9, what would you need to do? You would load 1 into the counter after you detect 9. So detect 9 and at that time load 1 into it. That's what you would do. All right, so over here the example is slightly different. What is it? We are trying to count from 3 to 12. So what would you need to do? Load 3 into counter when output is 12, when 12 is detected. So the moment 12 is detected, you will use that to load 3 into the counter. So I have to set it up such that A, B, C, D are indicating 3. And as you can see, A and B are 1, 1, C and D are 0, 0. So it is ready to load 3. I'm detecting 12, and 12 is the first time where you get what? 1, 1, 0, 0, right? that's 12. So I've taken up, these two are 1, by the way. So if those two are 1, that means that those two are 1. They go into a NAND gate. So as soon as QC and QD become 1, 1, I'm ready to load. The output as that is connected to the load input. I'm never clearing this, right? Clear is connected to high. I'm never clearing this. I have enabled the counter. ENP and ENT are connected to 1 as well. And that's how I would count from 3 to 12. And those counting sequences are shown over here. 3 to 12 to 3 to 12, and it will keep repeating. But those changes, those increments will happen at the positive edges of the clock. So, you know, the simple statement is load 3 into the counter when you detect 12. So in your studio today, you will say load 1 into the counter when you detect 9. But I highly recommend this particular slide as a resource for your studio today. Questions? Free running, start at an arbitrary value, stop at an arbitrary value, start and stop at an arbitrary value. So that's what we did today using a 74X163 chip. All right. Now let's talk about cascading counters. So if I can design a 4-bit counter using one 74X163 chip, I can design a 8-bit counter using two 74X163 chips. So all I would have to do is use that RCO output from the first stage to connect to the enable of the second stage. So only when the outputs of the first counter go to 1, 1, 1, 1, the next counter is enabled to go up one value, right? So you can see here. So this is what? This is a mod 256 counter, right? Because it's an 8-bit counter. So it's 0 to 255. And we are using two 74X163 chips here. Both of them are connected to the same clock, right? Both of them are being triggered by the same clock input. My clear is connected to a user input called reset_L. So I can use that to make all of these guys 0. Let me write that in red. So I can use this to make all of these guys 0. Maybe I may want to do that to make sure that I start at 0. Then I have load_L, which, you know, I can use this. Let me highlight that in blue. I can use this to load an arbitrary input into the counter, right? And that arbitrary input should be provided using D0, D1, D2, D3, D4, D5, D6, and D7. Then I have a counter enable input. The counter enable input is connected to both the enables of the first 74X163 chip. So if I make that 1, the first guy will start counting, which means that the Q0, Q1, Q2, Q3 will keep incrementing by 1 with respect to the positive edges of the clock input. Now let's take a look. What happens when it reaches 15, right? So suppose that you have started counting. Suppose that you have reset it. So everything is at 0 now. Then you have started counting, right? So once you have started counting, you have made sure that your reset is now inactive. And when it starts counting, how is it going to go? This is going to become 0, sorry, not 0, 1, right? 1, right? And then it will become 2. And then it will keep going, right? During that time, the other outputs are going to stay at 0, 0, 0, 0. So the second 74x163 is not going to count during this time. It is going to stay at 0, 0, 0, 0. This keeps incrementing, right? The first stage will keep incrementing. The second stage will stay at 0, 0, 0, 0. However, when this guy reaches 1, 1, 1, 1, RCO is going to become 1, which means that these guys are going to get active. When that happens, after the next positive edge of the clock, this guy will go to 1. And then what is going to be the next value? This will go to zeros now, right? So as you can see, this will increment. So let me write this. Increments by 1 every 16 cycles. You guys see that? So every time the first outputs, they go all through, right? 0, 0, 0, 0 all the way to 1, 1, 1, 1. When it completes one full cycle of those 16 counts, the next stage is going to increment by 1. And then it'll go to 2 at the it'll go to, let's see, it'll go to this after another 16 counts. That is essentially your 8-bit counter. Let me take a look at the chat box. Why would we not connect RCO4 to clock of the second this? Wouldn't that function the same? So it will function the same way. However, I want both the 74x163 to be triggered by the same clock source, which means that the clock source that gets it to 1, 1, 1, 1, I want that clock source to get that to increment by 1 after that happens, right? And during that cycle, this also needs to go to 0, 0, 0, 0, right? So they both need to respond to the same clock. One is incrementing by 1, the other is also incrementing by 1 at the same time. And I want them to be in sync. So I want them to respond to the same positive edge of the clock. I don't want any staggered behavior. Left count. All right. So in this case, if I don't connect to anything over here, what is going to happen? If I don't connect anything over here, it is going to keep counting from 0 to 255, 0 to 255, 0 to 255, and so on. But I could do other things with it, right? Like I could count from some arbitrary value to some arbitrary stop value. So for example, I could count, for example, from 60 to 128, right? So all I would have to do is, I would say load 60 into counter when 128 is detected. right? How do I load 60 into the counter? Let us try to take a look at this. How do I load 60 into the counter? So 60 is, help me out here. 60 is, let's see. I need 32 here. What else do I need? I need 16. I have reached 48 and I need 12 more. So I need 8 and 4, right? So that would be 1, 1, 1, 1, 2 and 1, right? Yes, you are right. So I think it's just this, right? If I need 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. I think 60 is that. Then how about 128? I think 128 you guys can tell me pretty easily. So why don't you guys tell me how 8-bit 128? Yes. 1 0 0 0 and 4 zeros. So I would essentially detect. So what is this? This guy is what? D7, D6, all the way to D0, right? So I would connect 0 0 1 1 1 1 0 0 to all those guys at the D's. Let me see. I have D0, D1, D2, D3 to be 0 0 1 1. So I have connected this to 0 0 1 1, and then D4, D5, D6, D7 are again 1 1 0 0. So I've got 1 1 0 0 here, right? So that's my loading sequence. And in order for me to detect 128, I can use Q7, right? I can use Q7 to indicate whether or not I have reached 128. So essentially, take a look at this. What I'll do is I will pick, say, a NOT gate right here, and connect Q7 to this, and the output of that can be connected to that, right? So what is going to happen? The moment Q7 goes to 1 for the first time, it is going to load 60 into the counter. So you have detected 128 and you have loaded 60 into the counter. So this one, now, instead of going from 0 to 255, you are using this to count from 60 to 128, right? But the only problem will be to start things off, right? So to start things off, you may use load manually to load 60 into the counter, or you can use reset to start at 0, then it'll go all the way to 128, but in the second round it'll come back to 60, and then it'll fall into that loop of 60 to 128. Questions about this? For first method, it will start as soon as you manually input 60 in the first loop. Well, yes. So if you load 60 by making sure that your load underscore L is active, then it will start at 60 and then it will be in that 60 to 128 loop. But for the second method, by clearing it first, it will start at, oh, no. If you are clearing first, then it will start from 0. It will start at 0, it will go all the way to 128, but it will come back to 60. So if you use clear to begin with, it will go 0, oh, sorry, too big. 0, 1, 128, but it will come back to 60. And then it will fall into that loop, 60 to 128 loop. Does that help your... Did I answer your question, Michael? So if you clear, everything will go to 0, right? But everything will go to 0. We are not detecting 0. So if everything goes to 0 and we start counting, it will go all the way to 128. We are detecting 128, and then that is the time we load 60 into the counter. It will start after finishing 0 to, and then start from 60. Yes. So in the second cycle, it will be in the correct desired cycle, 60 to 1 from the second one, from the second iteration. But for the first one, it will start initially from 60. Yeah, so there are two things, right? One is load and one is clear. You can use load initially to start at 60. But if you initially use clear, then it will start at 0. No matter where it starts, it will end at 128 and it will come back to 60 based on the current connections. All right. Okay, I hope that was helpful. Now we are trying to design a modulo 193 counter next. So in this example, we have two 74x163 chips that are cascaded together, but it is slightly, an interesting example, similar to what we did with the 60 to 128 example. So the way we are designing this modulo 193 counter is by going from, let us see what are we loading. We are loading over here, let's see, A, B, C, D, all are connected to 1. Over here, A and B are connected to 1, 1. These two guys are 0, 0. So the first question is, what is 1, 1, 1, 1, 1, 1, 0, 0? Because that is what we are, I wrote it all the way opposite because this is the least significant bit. So it should be 0, 0, 1, 1, 1, 1, 1, 1. Right? That is the least significant bit. This is the most significant bit. So 0, 0 followed by all those ones should come out to be, I believe, 63. Right? So we are loading 63 when something happens. What is that? When something happens, you see RCO of this guy is connected to the enable T of this guy. So that's your, cascading that we saw earlier. Then we are using this max count to detect 255, right? So when 255 occurs and the go for the counter is active, that means we are trying to count with this, we are going to do the reload. So that means we are going from 63 to 255. 63 to 255 is 193 different states for the counter. So that's what we are doing in this particular example. Load 63 into the counter when you detect 255. And we are detecting 255 by looking at RCO output of the second 163 chip. And everything else is connected, according to, their usual controls. Clock is, they are both clocked by the same clock source. We never want things to clear, so we have connected clears of both the chips to one input called reset_L. We may use that to initiate the counting sequence. One of the enables is connected to high. The other enable is what we are controlling here to make sure that the count reaches for the reloading operation. And the other inputs for 63 are connected to ones and zeros respectively to get you the 63 value. So this essentially says reload 63 when counter reaches 255, right? And go_L is active. All right, questions about this? Now, I hope that with this discussion, you guys have seen how you can start and stop from any arbitrary value. So in the previous example, we said 60 to 128, right? So I hope that you see you can start from any value to any value between 0 to 255. You could do anything with it, right? So I hope you gain that skill here to start at any arbitrary value and to stop at any arbitrary value. All we have to do is detect and load, and that's it. And for detecting things, we used a NOT gate here. However, in general, a NAND gate is very helpful in general. So if you wanted to you detect 1110, then so how would you detect 1110? I would simply take, say, let's call this QD, QC, QB, QA, right? If I wanted to detect this, I would simply put 1, 2, 3 into a NAND gate, right? And then that goes to the load input here. And I would put QD, QC, QB here. So I would use NAND gate, and when QC, QB, QD, C, and B reaches 111, that's when it will load whatever it needs to load into the counter. Okay. Next, we have an up and down counter. 74x163 only allows you to count up. 74x169 allows you to count up as well as down. So it's the up and down counter. It is. So let's walk through this. A lot of things are similar. Clock is a positive edge triggered counter. right? Positive edge triggered. Pin number 1 is the up and down input. So let me talk about that. Up/down. So when the signal is up, so if this is 1, then we are counting up, meaning 0, 1, 2, 3, 4, counting up. If this is 0, then we are counting down, 7, 6, 5, 4. You have an active low load input. You have active low enables, 2 of them. You have A, B, C, D as earlier. They can be used to load any arbitrary value into the counter. Active high inputs here. You have active high outputs here in QA, QB, QC, QD, exactly the same way as the previous chip. And you have your RCO, which is going to be slightly different because now you have counting up as well as counting down. When things were counting up in the previous example, RCO was active when the count reaches 1111. Now we are counting up as well as counting down. So is there a difference? Is there a different behavior for RCO? And the answer is yes. So let me say RCO is active low output, and while you are counting up, so if you are counting up, RCO becomes active. Active when counter is at 1111. So when output is 1111, this guy will become active if you are counting up. Or suppose you were counting down. If you were counting down, then RCO becomes active when it is 0000. So if this is 0 for counting down and the counter output is at 0000, that's when it will become active. RCO will become active there. So those statements should be helpful in order to understand the counting up and counting down process. These are also two different things. Two active low enables here. Earlier we had active high enables, and we talked about RCO, we talked about up and down input. Other things are essentially, why is RCO an active low output now? Well, it depends on the kind of inputs, right? So for this particular chip, the designers tried to achieve, went for an active low output so that they could connect directly. This particular output can be now connected directly to the active low enables or the active low load input, so that there's no need for another gate here. So I would say it was the designer's choice here in this one. All right, other questions? Now you can do the similar kind of cascading with this particular chip, right? 74X169. You can still put them one after the other, cascade using the RCO output. You can do a similar exercise as you did with the 74x163 in terms of cascading counters. Okay, so let us take a look here.